Now let's study a revised version of the simplex method. So recall that when we applied the simplex method, we created this Tableau using the components of this linear program. Call that the problem of a linear program is to find this x such that the to minimize the C transpose x such that ax equals to b and x is greater than or equal to 0, right? And to solve this using the simplex method, we put this matrix A as the top upper right corner of this tableau, and the B as this last column, and then C transpose, and then 0. Right? But when we apply the simplex method, we consider the inverse, we actually applied the row operations to this first m rows. Remember that this one is, recall that this one has m plus 1 rows and n plus 1 columns. And this first m rows are here. And the last one is just last row is just a single row here. So we applied the row operations to this first m rows, or basically applied the row operations to A and B. But this can be really expensive, especially when the m is much lower than, much smaller than n. Okay? For example, you have like 100 rows, but you have 2,000 or 5,000 columns. In this case, applying the row operations can be really expensive, and we actually wasted lots of things because when we consider the row operations applied to this matrix A, many of the columns they don't really become the basic column, okay, right? Because the purpose of doing this basic row operations is to convert one of the non-basic columns into a basic column. So only that column that becomes the new basic column is effective. All the other columns will stay non-basic, and it can be really wasteful to apply the row operations to those columns as well. Okay, so the revised simplex method is to avoid this kind of waste by working on the basic column or the new basic column only. So you keep the other columns of the matrix A unchanged. Okay, and to this end, remember that when we consider the basic columns of A, the A is considered as B times D, where B is the basic column that we're going to consider, and the D will have one of its columns to become the new column, basic column. So to this end, we only need to check the B inverse that is applied to this B and D, which together is the A matrix. We know that this is just equal to I and the B inverse times D. And we know that the basic column looks like this. Looks like identity matrix. I just rearrange them so that the first m columns are basic columns. And then we're going to choose one of them. We choose one of these columns to be the new basic column, right? So to this end, as long as we know what this B inverse is, and as long as we know what the B inverse is and what are the basic columns is, we can always create this kind of stuff, right? Because we know that which columns will be the basic columns, and we know what this B inverse is. So we can just apply the B inverse to that basic columns, and that part will be just identity. And then when I apply the B inverse to the rest, we'll just get something like this. Okay, so in this case, we only need to check what is the B inverse, current B inverse, and what are the current basic columns, and then what will be the new basic column. Okay, so that is the main idea of the revised simplex method. So in this case, what we really keep tracking is this B matrix, which is m by m. And we don't need to really apply the B inverse to the D at all. Since the D has m rows but n minus m columns, and n, if n is much bigger than m, then applying B inverse to D can be expensive, and it's not useful anyway, because only one of the columns in D is going to be the new basic column, and only that column is useful. All right. So to revise the simplex method to make it work, we start with the basic column and the basic variables. And in this case, the basic column, basic variables, a basic column will be just identity, right? We know that it will be just corresponding to the identity matrix, and the basic column, a basic variable will be just the B inverse times the current vector B. But in this case, the B is just in the identity matrix, so that the basic variable just the B itself. And recall that this is just because we know that current basic columns is this. I have the D, and the XD behind will be just the B, and this is B0. So when I multiply these two together, I will just get the B vector. Okay, and this is the A matrix. Okay, so that's our starting point. We initialize our B matrix as the identity, and also the B inverse will be identity as well. And all the rest columns of the matrix A are called D. And the current basic variable is just the vector B here. So we just keep tracking this, the B inverse and the current basic variables. And in case we're going to replace the one of these columns using another column from D as the new basic column, we'll just add that corresponding YQ later on. Okay. So now let's see how it's going to work. As I said, we're going to update this matrix. Initially, it was just identity and B, and later on, we will just update this this matrix. Essentially, we're just updating this B inverse, and also updating these basic variables. And also, we're going to keep tracking what are the current basic variables, or what are the index of the current basic variables, or the index of the basic columns. Okay, so now let's see. Remember that when we try to move on from one iteration to the next iteration of the simplex method, we need to find out two things. One is that we need to figure out which column of the matrix D will become the new basic column. Okay, or in other words, the corresponding component of the this RD matrix, RD vector. This will be the bottom row of the Tableau. We're going to look for the most negative value. And that most negative value will be corresponding to the XQ that is going to be replaced. It's going to be the new basic variable. And the column corresponding to the XQ in the matrix D will be the new basic column. Okay, so that's one thing. This is how we're going to decide which column of the matrix D will become a new basic column. Okay, and the second thing is we're going to see which old basic column will be removed, will be replaced by this new basic column. And to that end, we need to check the vector y0, which is the current basic variables, and divided by the YQ, and the Q is the index for the new basic variable. We're going to divide this YQ component wisely and see which is the smallest value. And that value is corresponding to the old basic column that is to be replaced. Okay, so as you can see, there are two, as I just mentioned, there are two things to do. First thing is to check this vector. And this vector is what we said, it will be the last row of the basic column, be the last row of the Tableau. And we check which one will be the most negative value. And to compute this value, as you can see, this will be just the most computation will be from here. And here we need to multiply this matrix B inverse that we will keep tracking to this vector CB, will be just the components of the vector C corresponding to the basic columns right now. Okay, so this will be the CB, which is actually a m-dimensional vector. So we need to multiply this m-dimensional vector by this matrix, m by m matrix. So this whole thing becomes a m-dimensional vector. It's a row vector, as you can see, because this is the row vector, this is the matrix. So we get a row vector here that is a one-dimensional m-dimensional vector. And then this D matrix, this is the only place that we need to compute or we need to invoke this D matrix. We said this part here is a m-dimensional row vector, and this D matrix here is a m by n matrix. So when we multiply them together, we will get n minus m dimensional row vector. So it's n minus m vector here. It's a row vector, and this is also a n minus m dimensional vector. So take the difference of them. So the key computation came from here, but this is cheap because we have a matrix vector multiplication, and then another matrix vector multiplication. So these two are both much cheaper than doing the row operations to the entire matrix D. Okay, so that is the first step, as I mentioned, which we will decide which, after this computation, we'll realize which xq is going to be the new basic variable, and we'll realize which column of the matrix D will become the new basic column. And then next, we're going to do the division of the y0 and the yq. Remember that originally there's the aq is the column of the matrix A, and corresponding to the new basic variable xq. So imagine that you have the A here, right? And there will be the Q's column will be the AQ. Okay, but you know that when we apply the basic row operations, the AQ will change. So what the AQ become will just the latest AQ will be just the latest the B inverse matrix times the original AQ vector. Okay, so whatever the AQ is, we just keep that. But since we're keep tracking this B inverse during the computation, so we know what this new what this column will become after applying this latest B inverse, and that is our YQ. And then we make a component-wise division of the Y0 and the YQ, and we would get m-dimensional vector here, and then we'll see which component is the smallest, and that variable is corresponding to the old basic variable or basic column to be replaced by this AQ. Okay, so once we see that, then we'll just need to update the B inverse matrix, and we collect the B inverse matrix we just had. We'll keep tracking, and then this Y0 is the current basic variable, and this YQ is the new basic column. And we need to make this something like the basic unit vector, like the 001 or 010, something like that. It depends on which basic column this YQ is to replace. Okay, so that is to be one of those. Okay, so we'll decide that. And once we finish this computation, we will update this Y inverse. At the same time, we will update this Y0. We will update this B inverse and also update this Y naught. And then we can move on to the next iteration. I'm going to start from here again. Okay, and then we're going to be having this updated B inverse. And this D will be still the remaining columns of the matrix A. Okay, just those columns not corresponding to the basic columns in the original matrix A, and the CB, CD are the same as before. Just the components of the original vector A, C corresponding to the basic variables, and the rest of the components in the vector C. Okay, I will repeat this procedure. Okay, so we set the key components or key ideas in this revised simplex method. Now we can apply this, or we can work on this example to see how this is executed step by step. Okay, so now look at this linear program. So we have a linear program that is to maximize the this objective function. It's a linear objective function of x1, x2, and the x1, x2 need to satisfy these two inequality constraints, and also the, as before, the x1, x2 need to be non-negative. Okay, so remember that the first step is to convert this into the standard form. We want something like the standard form, which is minimizing Cx subject to Ax equals to b and x greater than or equal to 0. Okay, so you know that if we want be minimizing the function, but we have maximizing the function here, just put a negative sign. So we put negative sign of this, and we'll get a minimization problem of this negative 3x1 and negative 5x2. Okay, now work on the constraints. We need to convert these two into this form. Okay, so apparently I can just add a slack variable. I call it x3, for example. I will add x3, and x3 will be non-negative, and x3 will be filling in the difference between the two sides. So that will be the slack variable to insert. And adding the x3, I'll make this equality constraint. Okay, and x3 will be greater than or equal to 0. And similarly, I'm going to work on with this. Well, since this side is actually bigger than this side, so I need to subtract some non-negative value, and that will be my x4. So I will subtract x4 from this left-hand side, and then I'll make these two sides equal. Okay, this is because I have a this inequality. So I need to subtract x4. Okay, so now I converted these two inequality constraints into two equality constraints, and I also made sure that the two new slack variables I added are non-negative. Okay, so now we'll just work on this standard form of a linear program, which is equivalent to the original problem here, and x3, x2 will be our slack variable to help us to convert this into the standard form. Okay, now we have four variables, x1 through x4, in this problem, but the objective function is still just involve the first two variables, which are the original two variables, x1 and x2 here. Okay, so now we're ready to apply the simplex method. Remember that the first step is to find out the basic solution for this problem. So that means we need to find out only two of this x1 through x4 as non-zeros, because we have two rows and the four variables. So the m equals to 2, the n equals to 4 right now, and the basic variable should have just two non-zeros, and another two variables will be just 0. So we need to decide a basic solution which has only two non-zero or two positive components. The other two components should be equal to 0, and such that it satisfies all these constraints. Okay, we need to find this x. That is a basic solution. Okay, and it should be R4. I want two variables to be positive. The other two variables, or two components of x to be positive, and the other two components of x to be 0. And also x satisfies this constraint. right here. Okay, or essentially just need it to satisfy these two because we already guarantee that all the components are non-zero, either positive or equal to 0. So it satisfies the inequality constraint. We just need to make sure that it satisfies this as well. Okay, remember that to accomplish this, we need to first work on the phase 1 of the simplex method, and that is also the we'll be considering a artificial problem, and for that artificial problem, we can easily get a basic solution, and then we can optimize that. We can solve that to obtain this basic solution. Okay, so recall how do we do the artificial problem? To compute the artificial problem, we need to work on this. Okay, we need to first find out if we can find a basic variable for this. Apparently, this is not easy to directly get, because previously, if we have this is less than or equal to 8, that will be easy because here we'll be having we'll be adding the x4, and then we can just set x3 to be 4 and x4 to be 8, and that will be a basic variable. But right now, since we have x minus x4 here, so we cannot set this x4, this x negative 8, because that negative value is not allowed in the basic variable. It's not allowed in the basic solution. So that's why we need to consider, remember I have the ax equals to b, and if it doesn't give us a basic variable, we just need to consider adding the x plus the y equals to b, making sure that the b is non-negative. We just need to add this y vector. Y is an m-dimensional vector, and initially we can just set y equals to b itself, and this a and y together, x and y together is the current variable we're trying to solve in the artificial problem. But here, as you can see, we can actually save one of those y's. So we don't need two y's because we already have one of this as the basic variable. So the x3 is already equal to, we can set it to equal to 4. And that's already okay. And now we just need one more artificial variable to be introduced in this equation. So that one we call it y1. And we can add the y1. So this one is already okay. So we can just divide the y1 in the second one and make sure that y1 is equal to 8. And in this case, we will have this this artificial problem. We'll be having this minimizing the y1 subject to minimizing y1 subject to the constraint, which are the x1 plus x2 plus x3 equals to 4, and the 5x1 plus 3x2 minus x3 x4 plus y1 equals to 8. Okay, and also x1 through x4, they need to be non-negative, and also the y1 needs to be non-negative. That will be our artificial problem to solve. And after solving this, the y1, since y1 is negative, the minimum value of the objective function must be that the y1 equals 0. And in that case, this is 0. And we found a basic solution that makes sure that the x1 through x4, only two of them will be non-zero. And also the x1 and x4 will satisfy this original constraint here because y1 is equal to 0 when it is minimized. Okay, so that is the artificial problem we're going to solve. For notation convenience, I will just call this y1 to be the additional variable x5 in addition to the existing variables x1 through x4. Okay, I'll just call it x5, and that is actually the y1. We're going to minimize this x5 such that all the variables we are considering here is x1 through x4, but the objective function here is only involving the x5. And we're going to find the minimizer for this first. Well, the purpose of, as we said, the purpose of introducing this x5 is that right now there is a obvious or apparent basic solution, which is this is just setting this as 4 and this as 8. Okay, just equal to the right hand side, and then we set x1, x2, and x4 to be 0. So this will be a basic solution because it satisfies all these two, and also they're non-negative, and also only 2 of them, which is equal to the number of constraints. There are only 2 positive values, and we can start from here and apply the simplex method, or in this case, we're going to apply the revised simplex method. Okay, so now that's the setup of the artificial problem, and we're going to consider the Tableau. The Tableau is as we said, it is going to give us a matrix. We're going to look at the matrix A in this artificial problem. They should be a 2x5 matrix, 2 equality constraints with 5 variables. So this should be a 2x5 matrix, and the B will be this 4, 8. And the C vector, as you can see here, C vector should be 0, 0, 0, 0, 1, because only the x5 has a coefficient 1, or the others are 0. So that's going to be our Tableau. So we'll just replace the compute or place the Tableau here. This part is the matrix A, which is the coefficients of the equality constraints. As you can see, the first equality constraints gives us this 1, 1, 1, and 0 for the other two. And then the next one gives us the 5, 3, 0 for x3, and -1 for x4, and then 1 for x5. So that's 5, 3, 0, -1, and 1. And as we said, the basic variables right now will be 4 and 8. And this part here gives us the C, which is the coefficients for the objective function. Okay, and the 0 will be the current objective function value. Okay, so this is the Tableau we're going to start with. Well, we can apply the original simplex method, but we said that this may not be efficient since we just have 2 rows but 5 columns. We don't need to apply the row operations to the 2 rows, entire 2 rows. Instead, we only need to work on the B inverse to keep tracking of the B inverse and the basic variable. That'll be fine. So here, as you can see, the basic columns will be x3 and x5 because this is the identity matrix, and this will be our y0, current y0. This will be our current B inverse. Okay. Now we're going to continue. So as we said, this B inverse is the identity matrix. The y0, which is the basic variable, will be the 4 and 8. And the corresponding basic variable, as you can see, is corresponding to x3 and x5. So I should choose x3 to be 4 and x5 to be 8, because this x3 is corresponding to this one here, and that is corresponding to 4. And here is 1 is corresponding to 8. So I should choose my x3 to be 4 and choose my x5 to be 8. Okay, so that is our basic variables, x3 and x4. And now recall that for each iteration, the first thing we need to do is to compute this RD to figure out what is the new bottom row of this Tableau. We need to see what this bottom row will be, and the most negative value here will be telling us the new basic variable. Okay, so that's the first step. So we compute the RD, as sort of the formula is the CD minus CB B inverse times D. Okay, remember that the CB is the coefficients of in the vector C corresponding to the basic variables. And now, as you can see, the x3 and x4, they are the basic variables. So this 0 and 1 will be the CB vector. Okay, and the rest will be the CD vector, which is this, this, and then this. This will be the CD, okay, corresponding to these three values. And then these two will be inside the CB vector. Okay, and the B is currently, or B inverse is currently the identity matrix, which is corresponding to this column. Okay, that will be 1, 0, 0, 1. Okay, and the D matrix will be the remaining columns of the matrix A, which will be this part and then this part. These two together is the D. Just keep these three columns here. That will be the D vector. Okay, now we have everything, right? The CD, as we showed, is the zero vector. The CB is the 0, 1 vector. The B inverse is current identity matrix. The D is the remaining three columns in the matrix A. So we just need to make a modification, computation of that. So apparently, when we multiply these two together, we'll just keep this one because it's the identity matrix. So we're going to multiply the 0, 1. That is the result of this one. And to multiply this row vector to this matrix. And apparently, we're just keeping the last row, the second row of this matrix, right? When we multiply it by 0, 1. So we're subtracting the 5, 3, and -1 from the 0 vector CD. And we'll get -5, -3, and 1. And this will be the current bottom row of the Tableau. And they are corresponding to they should be the values below the non-basic columns, which means that they're the values corresponding to the x1, x2, and x4. Because the current non-basic columns will be this column, or this column, this column, and this column. So we're going to replace the value here, here, and here by this new variable RD. And that's a -5, -3, and 1. So that means after we do the row operation, if we didn't do this revised simplex method, we just do the original simplex method, what happens is we're going to do the basic row operations. Right now, we don't need to do the basic row operations for the first two rows because they're already finished. The last row, we need to do the basic row operation such that this will be 0 below the 1, and this should be 0 below the 1. So that's why we need to subtract the second row from the last row here to get this new basic column. So as you can see, when we subtract the second row from the last row, we get -5 here, -3 here, and a 1 here. So that's why we have the -5, 3, and 1 as the values for the last row. And then we're going to look for the most negative value, if there's any. So apparently the -5 is the most negative value. And that is corresponding to the R1, which means that X1 will be the new basic column, which means that I'm going to use this as a new basic column. I'm going to replace one of these two and to form the new basic columns. Okay, so just replace replace one of these two last columns by the first column. Okay, so now how do we do that? We need to figure out which of the two columns are going to be replaced, right? So in this case, we need to figure out the currently we have this this column, which is supposed to be the B inverse times A1. But the B inverse right now is the identity matrix. So this will be our Y1. It will be the B inverse times A1. So so that means the Y1 is just equal to A1 for this iteration, for the first iteration. Okay, and then we're going to divide, which this This is the y0. We're going to divide the y0 by y1 component-wisely and see the smallest value. And that will be the corresponding to either A3 or A5 to be replaced. Okay, we decide to use the A1 as a new basic column, but we need to figure out which one of the A3 and A5 is going to be replaced by A1. And this is how we're going to find it out. Okay, so as we said, the y1 vector is the B inverse times A1, and the B inverse just that in the matrix. A1 is right now 1, 5. So I use this to denote the vector, column vector 1, 5. And then we make a component-wise division of y0 and the y1. So the y0, recall that y0 is this, so it's 4, 8. The y1 is 1, 5. So when we divide 4, 8 by 1, 5, this is not really a rigorous way of writing this, because we cannot really divide two vectors. But here it just means that I'm going to divide two vectors component-wisely. And this gives us 4 and 8 over 5. Okay, and that is why we have this 4 and 8 over 5. So we see which one is smallest. That's smaller, right? That's the smallest value. So we're going to use the column corresponding to this A over 5 as the basic column to be replaced. Okay, so as we said, this second one will be corresponding to the one, the second one here is corresponding to the one to be replaced. So remember, this one is corresponding to the x3 and x5. So that means x5 is going to be removed. And that means the fifth column will going to be replaced by this column. That means I want to apply the basic row operations such that this one becomes 0 and 1. And whatever happens to this, I don't care anymore, because this will be my new basic column. And this one will join, it will join this one here. So this one will join this one together, will be the new basic column. And that's why I want this to be 0, 1. And together, these two will be added in the matrix. Okay, so now we have decided which one will be the new basic variable and which old basic variable which will be replaced. In this step, we're going to figure out what happens when we apply the basic row operations to this y0 and y1. So that means what kind of operations we're going to do to this such that it becomes 0 and 1. And we're going to keep tracking of this one and this one C, because this will be the row operations will be in the original simplex method. The row operation will be applied to the older rows, so that this B will be replaced, will be changing. Will be a new basic, will be the new basic variables. Okay, so that's also changing, and that's changing along with this. So what happens to this change is that we're going to apply basic row operations. We can think that is adding to the B inverse matrix, so that this first column becomes 0, 1. And what happens to the last one will be also changed along with the first one. So that's why we place the first current B inverse matrix, which is the this matrix here, and the y0 is the 4, 8. Remember that. The y1 is the current A1, that is the 1, 5. Okay, and then we're going to, our goal is to change this into 0, 1. Okay, change this into 0, 1. So to do that, we can multiply the last row, the second row, by 1 over 5, and then subtract from the first row. Because after multiply 1 over 5, this will become 1, and subtract this from the first row, we'll cancel this one here. Okay, so the last row multiplied by 1 over 5 becomes this. Okay, that's obvious. And then we subtract this from this row, and we'll get this part. Okay, the first one doesn't change because it's 0 below it, but the other three will change. and this one becomes 0. These two become these two values. Okay, that's the basic row variable. So after doing this, the new B inverse will be this part. Will be this. Okay, will be this one. So it's this is what happens when we apply the row operations in the to this Tableau. When we do this in the original simplex method, the B inverse actually becomes this, because that's what we need to do. That's the effect of the basic row operations, and we'll keep tracking of that. We merge that into the B matrix or B inverse matrix. So originally it was identity matrix. Now it becomes this. Okay, and now the basic variables will be what happens to this, whatever you have left for the y0 vector, and that becomes this. So that is our current basic variables. Okay, so what this means is that the B inverse is updated to this matrix, and the basic variables are updated to this. And we also know what are the current basic variables, because that we replaced the x4, sorry, we replaced x5 by x1, right? We replaced this one by this one. Okay, so that's why we have the basic variables right now. Then that should be corresponding to the that would be corresponding to the current basic variables. Okay, so here I think I have the table. Remove that. So it should be x corresponding to x1 and x3. Or actually, I should write in the x. I read as x3 and x1 because here this x3 is corresponding to this component. That is the first component of the basic variable. And this becomes 0, 1. So this 1 is corresponding to the second component of that. That's why I should write this as x3, x1. Just replace this by 1. Okay, and we know that this is corresponding to 12 over 8. And that this is second one is corresponding to 8 over 5. Okay, so that will be my basic variable. So these two will be non-zeros, and the remaining ones, which are x2 and x4 and x5, they will be 0. Okay, so that's my current solution. So I'm going to, this is what happens when we finish the first round and the second round. We're going to do this computation one more time. And the current CB, as we said, is corresponding to the these two variables, which are the C3 and the C1. But C3 and C1, let's see what that is. So this is the C vector. C3 is this, C1 is this. So it will be 0, 0. So here I will have 0, 0. And the B inverse is the current B inverse here. So I'm going to put this back in here. That's this one. And D will be the remaining columns. So which will be, the D will be the remaining columns, so that will be this, this, and then this. I think I have a table here as well. So this should be the, so it should be not this one. It should be ones. I should keep the 1, 3, 0, negative 1, and this one will be become the new one. So see what the one is. It's this. The new basic column. is changed to 0, 1. So this should be 1, 3, 0, negative 1, and then 1. Okay, so we can make this computation. But as you can see, we have this 0 times this. So that will be a 0 vector. We'll multiply this by this matrix, we'll get 0 vector. Okay, it will be just a 3-dimensional 0 vector. And subtracted from this, we'll just get the original vector here, which is 0, 0, 1. Okay, and they're corresponding to the non-basic variables right now, which are x2, x2, x3, x2, x4, and x5. So it's x3, x2, x4, and x5. Okay, and there will be the current RD. All right, and that is the computation of the RD. But as you can see, the RD is non-negative value. We cannot see any negative values from here. So that means we'll stop here, and we should already get the basic variables right now, since the x1, x4, x3 are these two. Okay, and the remaining ones will be 0. And we can plug this in back into the this problem. We'll see that satisfies this. So recall that what is the current one we got? 8 over 5 for the x1, 12 over 5, 12 over 8 should be the x3. So this x1, x3. So we can plug this back into the problem, x3 and x1, x3. So remember, x1 equals to 8 over 5, x3 is equal to 12 over 8, and x2 equals to x4 equals to x5 will be equal to 0. All right, so that's why when we plug this in, as you can see, the first row gives us, we plug in this, and then this, the sum of these two, oh, sorry, it should be 5, right? Yeah, 12 over 5, sorry. It should be 12 over 5. Now this is correct. Should be 12 over 5. Since we have 12 over 5 here, and 8 over 5 for this. So this is correct. So I'm going to over 5. So we add these two up, x1, x3. The x1, x3 sum together will be 4. As you can see, it's 20 over 5 is 4. And then we'll plug in this here, and then this into, or it doesn't appear here at all. So all these three are 0. So I just need to multiply 5 to this 8 over 5, I've got 8. And apparently, these are not negative. That satisfy this, and it's a basic solution because only have two positive values, and that is corresponding to the number 2, which is the number of equality constraints now. Okay, so we reach to the basic column, basic solution, and that is going to give us the initial value for the phase 2. Okay, so now let's work on the phase 2. So for the phase 2, we don't need to worry about the x4, 5 anymore because we already it's already used. We already used it, and it already helped us to find out the basic solution, and that gives us the basic solution list as we saw earlier. Okay, and now look at the current Tableau, which is the A matrix, and this right-hand side vector B. Basic vectors, and this will be your C column. Okay, and that is become from the original problem, since we have -3 and -5 in front of the x1, x2. So we have -3, -5, 0, 0. And for the first row, we have 1, 1, 1, x4 is 0. So it's 1, 1, 1, 0 in the first row of the matrix A. and 5, 0, 0, 5, 3, 0, negative 1 for the second row of the matrix A. And this will be our right-hand side. Okay, so that is the matrix A, C, and the B vector. Okay, and recall that after when we finish the first phase, this is our basic solution, and the B inverse, which will keep tracking of that, it became this one, right? That's our B inverse matrix, and the Y0 was this. Okay, so now we can move on to the first iteration. Okay, so again, we first need to check the D vector. So we need to look at what happens to this one. What should happen to this one? Okay, as we said, this x3 and x1 are current basic variables. So I will need this 1, 0 here, no problem. And I also need this as 0, 1. And then all the others will be 0. And then we'll see what happens to this 2. And this will be our RD. Okay. So the RD is computed by this formula, right? The CD is what we have left for this, which is negative 5 and 0. That's our current one. So I'll keep the negative 5 and 0 here. And the CB is the one here. So this two. Okay, so that's this. And also the D matrix will be this and this. Okay, so that's 1, 3 and the 0, 1. So when we do the computation, we will figure out that this is equal to that. Okay, that's our R2 and R4. That's what these two becomes. These two become. Okay, so let's try to do that. Let's try that. I think probably these two should be switched. Let me see. If I do this, if I do the current one, I will get negative 3, 0, 1, 0, negative 1 over 5, and 5. So I'm thinking that should be 0, 3, negative 3. Let me do that. So I think this should be. So this should be, or just remove this, should be negative 0, negative 3. I'm going to compute 0, negative 3 here. Multiply this 2, then this 1, 3, 0, negative 1. Yeah. And then when I multiply these two together, I'll get the first one gives me just a 0. The second one is I need to multiply this to the column here. So it's negative 3 over 5. And then I multiply this 1, 3, 0, negative 1. I will get the first one is still multiply this and then this. I'll get negative 9 over 5. And then multiply this row to the last column, I'll get 3 over 5. Okay, and then I take the difference between the CD vector here and then this. What I will get is negative 5, 0, minus negative 8, negative 9 over 5, and 3 over 5. Yeah, so that's giving me the negative 5 plus 5 over 9. That's my first component. Let's see what that is. Negative 25 plus 9 over 5. And that is 5, negative 25 plus 9. Remember that is negative 16 over 5. Okay, so that should be my first component here, negative 16 over 5. And the second component is easy, there's 0 minus 0.5, so it would be negative 0.5. So that's my vector, and this should be correct, but this one should be switched, it should be 0, negative 3. The reason is because the B inverse matrix corresponding to the two basic columns x3 and x1. So x3 goes first, x1 goes second. So their corresponding coefficients will be x3, c3 and c1. So that's why I should have 0, negative 3 here. All right, so that's this one. Okay, and then we know that this will be corresponding to the R2 and R4, and that will be the new value here, R2 and R4. And then we'll look for the most negative value, which is apparently the this one is more negative. So x2 will be a new basic variable, or a2 will be a new basic column. And let's see which one is going to replace. The current column, base a2 column, will be the B inverse times a2. And that's our y2 vector, right? So that means we have reached so far in that the A is supposed to be changed to the B inverse times A. And the B inverse right now is the matrix we're keeping tracking. And we know that we're going to use this as a new basic column. So let's see what is the current value of this. And it should be equal to the B inverse times this column. So the B inverse is this one here. And the A2 column is the 1, 3. So let's compute that. The Y2 should be equal to the B inverse times the A2. And the B inverse is the 1, negative 1, 5, 0, 1, 5 times A2, which is 1, 3. So when we multiply this together, we can see that it is 1 minus 3 over 5. And the last row gives us the 3 over 5. So together, it's just a 2 over 5 and a 3 over 5. So that's the Y2 right now. So that's the Y2. Okay, and then this is the Y2. The Y0 was call that, or Y0 is the current value here, right? So I just need to make a component-wise division of Y0 and the Y2. So the Y0 is 12 over 8 over 5 and 8 over 5. So let's make a component-wise division. The Y0, Y2 will be equal to 12 over 5, 8 over 5 divided by this. Remember that this is really informal notation. You can never write this in your own homework or paper. It's not rigorous. But this one gives us the 6 in the 8 over 3. So that means this. Yeah, that's this Y0 over Y1. Okay, and compare these two, we see this one is smaller. So that means, this one is corresponding to the this first. So x2 will be the new variable, but this one should be corresponding to x3. This one corresponding to x1. Okay, I consider the order of y0. We said that this is corresponding to x3. This is corresponding to x1. We make a component-wise division. This is still second component is still corresponding to x1. So that means we're going to replace x1 or a1 by the a2. So a1 was the basic column, but right now we replace it by a2, which will be a new basic column. Okay, so now, as I said, how do we do that? We're going to update the B inverse matrix. The Y0 is this, the Y2 is this, right? We know that we are going to make A2 as a new base column. So this is the current A2 after the most updated A2. It actually just B inverse times the original A2, right? This is how we compute the Y2. And now see here, this I want this to be 0, 1. And whatever happens to the others, I don't care, because there will be, after the computation, we'll just keep them. Okay, so basic row operation to this. How do I make this how do I make this become 0, 1? As you can see, I just multiply the second row by 5 over 3, and then I'll get this row here. So 5 over 3, 5 over 3 to the first 1 over 5 becomes 1 over 3, and then 5 over 5, 8 over 5 times 5 over 3 becomes 8 over 3, and the last one becomes 1. And then we need to multiply this row by 5 over 2, multiply this row by 5 over 2, and subtract it from the first row, and then we will get this. Okay, or you can directly multiply this row by 2 over 3, and then subtract it from the first row. It's the same. Okay, after do the computation, we'll get this part, and this first part will be our current updated B inverse, and this one will be the updated Y naught, or the basic variables. Okay, so as we said, this is the B inverse. This will be the current updated basic variables. But remember that we had x3, x1, but replaced x1 by x2. So this first one is corresponding to x3, second one is corresponding to x2. Okay, and the value of them is this x3, this x2. Okay, as we showed here. And B is this, as we said. And now we can move on to the next iteration. And again, the first step in this iteration is to compute this. And then we're going to compute the CD and CB B inverse D. Okay, so the B inverse is this, as we just updated. The D column will be the x1, x4, because x2, x3 are basic columns. So the D will be corresponding to the non-basic columns. And that's giving us, remember that's this and then this. Okay, x1, x4. So 1, 5, 0, negative 1. So it's 1, 5, 0, negative 1. And then the CB will be the coefficient in front of the x3 and x2. So it should be C3 and C2. So C3, C2 should be this. Or it should be 0, negative 5 again. Yeah, that should be 0, negative 5. This is correct here. Right? It's corresponding to C3, C2. Okay, and apparently the C1, C4 will be just negative 3, 0. Okay, so that's what we put it here. Negative 3, 0 will be the CD, and 0, negative 5 will be this. And then we can do the computation. As you can see, when I multiply these two together, this should be equal to 0. And then 0 times negative 1/3, and negative 5 times 1/3, which gives me negative 5/3. And then I multiply this to this matrix. So let's see. Just add it here. So this becomes, whole thing becomes that. And then I will get, or I just get a vector 0 times 1 plus negative 5/3 times 5, which is 25 over 3, and then negative 5 over 3. Okay, and then I'm going to subtract this from the negative 3 and 0. So negative 3 and 0, subtract this minus this. Okay, apparently I need negative 3 plus 25. 25 over 3. Okay, so that is, we had something similar before. This is 3, and that's -9 plus 25. That's just giving us 16 over 3. And then 0 minus -5 over 3, that would be positive 5 over 3. Is that right? Oh, sorry, it should be negative. Oh, it's negative. So that should get 5 over 3. So it should be 5 over 3. So when I do this computation, I will get 16 over 3 and -5 over 3. Okay, that's our R1 and R4 now. So it's corresponding to the new variable here and here. So it should be these two values. Okay, so that's the R1 and R4. Okay, now look at these two values. This is still negative, so I can still continue to improve the objective function. In the x4, it will be a new basic variable, and the corresponding a4 will be a new basic column. And then we're going to decide which one is going to replace, which one of x2 and x3 we will replace. So to that end, we first compute the y4, and that will be the updated a4 column. So the a4 originally was this will be the a4, and the current B inverse is this, right? Where is this one? So we just now need to multiply this by the a4, which is 0, -1. So we just keep the second column and change the sign. So the y4 equals to 0, -1, -1/3, 0, 1/3 times the a4, which is 0, -1. So that's why we got 1 over 3 and the -1 over 3. Okay, that's our a4. And now we can see that the y0, current y0 is what? Current y0 is what's current y0 is this, right? 4/3 and 8/3. So this is the 4/3, 8/3. And then we would just need to make a component-wise division of y0 and y4. We'll get it will be y4. It should be giving us 4 and -8. It should be our y0 over y4. Okay, and I can see the smallest positive value is 4 here. So, and this one was corresponding to x3, and this corresponding to x2. So we're going to replace the x3. x3 will not be a basic variable anymore, and we replace that by, as we said earlier, we'll be replacing that by x4, or the a4 will be a new basic column. The a3 is not a basic column anymore. Okay, so now I can do the basic row operations. So this will be the B inverse. The current y0 is this. The current y2 is this, right? Sorry, it should be yeah, it should be y4 here. So this will be y2, y4 here, right? Is this one. And then this is the B, as we said, this is the B inverse, is current basic variables. And what we going to do is to make this 0, 1. Okay, since this will be our new basic column. So I make this 0, 1. As apply the basic row operations, apparently I need to multiply -3 on the last row, and I will get this. There are lots of typos here. So it should be okay. Actually, it's not a problem. It's actually correct. This I should change. I should replace the x3 by x4. So x3 is corresponding to the first one. It's corresponding to this one. So I'll need to make this as 1, 0. So to make this as 1, 0, I need to multiply the first row by 3, and then I also add these two. I will cancel up this, make this 0. So multiply the first row by 3, I will get this. So just multiply 3, and I will get a 1 here. And then adding these two rows, I will see that this is the 1, this becomes 1, this becomes 0, this 2 become 12 over 3, which is 4, and then adding these two will be giving us 0. So that's this matrix. So I will need to make this become 1, 0. Okay, so now this will be the B inverse, and this will become the current y0. So this is the 1, 0. 1 is corresponding to x4, and the 4 is corresponding to x2. Okay, right? So that's the current value. So it should be, sorry, it should be multiplied by 4. So it should be 4 here. Right? Multiply the first row by 3, so I get this. And that's why we have this as our y0, this is our B inverse, and this as our y0, B inverse and y0. And now that's become this and this. Okay, as we said, this is x4, this is x2, and they're both 4. Now we can check the current RD vector. So the RD vector will be the difference between the two, right? And we can see that this part is the B inverse and the CB. So let's see what happens to that. The CB vector is corresponding to the current basic variables, which are these x4 and x2. So they should be CB. It should be 0, -5. And the others is -3 and 0. Okay, so that's this. This should be 0 and -5, and -3, 0 should be corresponding to that. So this is this, and then this is this. The B inverse, as we said, is this matrix. So I just put it here. And the current base column will be the A1 and A3. So it will be this. You can check the first and third column of the matrix. It will be this. So now we'll make a computation. We multiply this to this column. We'll get -5. So I'll get, just directly write it here, will be -5. And when I multiply 0, -5, and -1, 0, I will just get 0. So when I multiply this to the 1150, I will get -1, -1, -5, -5. Okay, so that's what happens when I multiply all these three together. The first two here gives me this vector, and then I multiply this matrix one more time, I get this. So this whole thing here just become -5, -5. So when I subtract it from -3 and 0, I've got 2, 5. Okay, I'll get 2, 5. And that is our x1, x3. And that's corresponding to R1 and R3, right? R1, R3 will be the C vector corresponding to the bottom row of the tableau corresponding to the A1 column and the A3 column. And now up to this point, we can see that these two are both positive values. There's no negative value, so we cannot further decrease the function value. is already optimal. Okay, so when we finish it, we can realize that x1, x3, the xy vector is x1, x2, x3, and x4. We said that x1 and x3 are 0, x4 and x2 are both 4. So that's this. This is our basic variable for the standard form of the problem. But the original problem only involves the x1, x2. So that's why the optimal solution for the original problem is 0 and 4. 0 and 4. And also, if this is actually what we really need from the linear program, right? We most linear need the minimizer. But if you want the original objective function value, we know that this should be, so here for this problem, this should be 0, 4, and this is 0, this is 4. But for the original problem, this should be 0 and this should be 4. So that means the solution to this one is x equals to x1 and x2, and that is equal to 0 and 4. Okay, so apparently it satisfies this non-negative. It satisfies this first one because you plug in 0 and 4 is less than or equal to 4. Then plugging this into here, you see that it's 0 and 4, that's 12, which is bigger than 8. And then when we plug this into the objective function, we'll get 20. So that's maximum function value is 20. But the maximizer is 0 and 4. Okay, and it satisfies all these constraints. Okay, that's the final solution for the problem. Okay, so that is the end of this revised simplex method.